All right, so the next chapter in the Klein textbook is all about chirality and stereoisomerism. But before we talk about stereoisomerism, we need to talk about chirality first. And chirality is pretty interesting. It's related to the handedness of molecules, and I'll tell you what I mean by that. So I'll say oftentimes molecules have handedness. It's kind of my made-up word here. And so what I mean by this is, if you look at your left hand and your right hand, are they the same? Kind of, right? However, if you got two right-hand gloves from the store, would you be very happy? No. So yeah, they look the same. You still have thumbs and index fingers and pinky fingers on your hands, kind of in the same order. But how are they different from one another? They're mirror images of one another. That's exactly what's going on here. So I'll take an example where we can see this mirror image. And I'm going to make up a molecule here. All right. If we think about the mirror kind of being this blue line right here, let's draw the mirror image of this molecule. All right. So if we have the mirror image, we would still have a hydrogen that's a dash connected to a carbon. The fluorine would be reflected as a wedge. The bromine would be going up, and the chlorine would be going out to the right. Are these the same molecules? It's confusing, right? You look at them and you're like, well, they have the same constituents. How could they not be the same? Well, my challenge for you is build this with your model kit and try to overlay them atom for atom. They are not the same. In the same way that your left hand's not the same as your right hand. Even though they look similar, they are not the same, and you can't overlay them finger for finger with your hands. So same idea here. So these are non-superimposable mirror images. It's the fancy science term. That means that both compounds are chiral. So anytime you have a molecule where you draw the mirror image of it and it's not the same, meaning you can't overlay it atom for atom, you're looking at a chiral molecule or a chiral compound. All right, so let's do some practice. All right. Let's determine if this molecule is chiral. So what should we do as our first approach? Draw the mirror image. Okay, so if we're going to draw the mirror image, I'll do it again with this blue line here. And then I'll do the mirror in blue just so we can clearly see that this is our new drawing in blue. Oops, this should be a wedge. We'll just go ahead and we'll draw the mirror. All right, so my question for you is, are these the same molecules or are they different molecules, and why? So check with your neighbor and see if you agree. All right, so let's do a check-in. How many of you think they're the same molecule? A decent percentage of the class? I agree with you. If I take this molecule and I just rotate it, meaning spin it on the board, it would look like this. And then if we compare both of these are the exact same, right? So these are the same compounds. meaning these are not chiral. The common mistake organic chemistry students make is they think anytime you see a molecule with dashes and wedges, that's your clue that you're looking at a chiral compound. No, not always. It's a good clue that it might be, but in this case we see an example where the mirror image is the exact same. So don't always assume that because you're seeing dashes and wedges that we're talking about a chiral compound. All right, let's try another one. We'll keep on doing similar ones. Let's do this one. Looks like this. Let's determine if this is a chiral compound. So just like before, what I would do is I would draw a mirror plane, and I would try to draw the reflection on the right-hand side. And I'd say, all right, that would still be reflected as a wedge. This would be reflected as a dash. Are these the same compounds? Okay, let's try spinning it like this. Okay, so again, we'll rotate it kind of like we did the one above. Are these the same? What if we flip it over? So let's say flip like a pancake. Oops, that's not pancake. Okay, if we flip this like a pancake, what will happen to the dash on the top? Meaning, what will happen to this one if I flip it over? Okay, it would be a wedge, right? Which is good. All right, and what about over here? What would this become? A dash, but if we flip it like a pancake, which side would it be on? The left side. Are these the same? So if I look at this versus that, is the black one the same as any of the ones we've drawn on the right so far? No, they're not the same at all. So these are not the same. Specifically, they are not superimposable. Therefore, the original compound is chiral. Does that make sense? It is tricky. Like I said, when I took this course, I felt very three-dimensionally challenged, and I was like, I have no idea what's going on. What's the strategy when that happens? Model kits. So I had to build a lot of model kits, physically lay them down on my desk, build the mirror image model, then rotate it in space and try to stack them perfectly atom by atom on top of one another in order to see what was going on. When you do that a certain number of times, all of a sudden you start to see these trends and it becomes a lot easier. All right, let's do one more. Let's do this one, a little bit different. Alkene. So we got a double bond there. Would this be a chiral compound? Let's try it. So mirror image, I'll draw like that. I'll draw the mirror compound in blue. Are these the same? I'd say they're the same, right? We could overlay these atom for atom. Therefore, these are not chiral. So it does get a little bit tricky. Like I said, the most common mistake I see, having taught this class for years, is students immediately jump onto the dashes and wedges. And they say, well, if there's a dash or a wedge, that means that it must be chiral, right? But we just saw an example in this first part that proves that wrong. So instead of thinking about dashes and wedges, think about mirror images. Mirror images are what we should be looking at when determining whether or not a compound's chiral or not. Yep?
If we took this one that we're looking at now, and instead of a pentane, it being a hexane, where the dashes and the wedges become axial and equatorial, does that change it?
So your question was about cyclohexanes with substituents coming off in axial versus equatorial. We'll go on and do practice with that too. It does matter a little bit because we do have to think about chair conformations, but we can always do chair flips and invert conformations as well, right? So we do need to keep that in mind. All right, I will give you a hint though. If you ever have an internal plane of symmetry, you cannot be chiral. All right, so let's go and apply this internal mirror plane to the one right above. You see how right above, if we cut this down the middle, the left-hand side is the same as the right-hand side? Therefore, it has an internal mirror plane. Can't be chiral because of that. All right, let's do the one right above here. Does this have an internal mirror plane? Can we cut it in half and have the one side be the same as the other? Well, what about if we do this? Is one side the same as the other? No, why? One's a wedge, one's a dash for the methyl groups. All right, what about up here? Does this have an internal mirror plane? Yes, so even though it has dashes and wedges, those wedges are actually mirror images of one another. Therefore, this has an internal mirror plane. You can use this as a pretty quick tool for identifying when a compound with dashes and wedges is not chiral. All right, so let's go on to the next part. Next part's talking about stereocenters. The book will sometimes use the term chiral center. I personally don't like using the term chiral center because I feel like it's confusing for students, because sometimes you can have chiral centers in a non-chiral compound, and that to me just makes your head spin. So I refer to these as stereocenters. All right, so let's define what a stereocenter is. All right, so a stereocenter is an atom that has 4 different substituents coming off of it. And one can be a lone pair. Can we ever have 2 lone pair substituents off of a stereocenter? No, because all 4 need to be different, right? So you can only ever theoretically have 1 lone pair. I'm going to put an asterisk here. Nitrogen lone pairs don't count. Does anybody know why? If we think about ammonia, right? Ammonia is NH3. It has 3 hydrogens underneath and a lone pair sticking up. Ammonia is kind of weird. The electrons in the lone pair will actually tunnel through nitrogen, and then it will invert like an umbrella, flipping inside out really fast. Nitrogen behaves very strangely. When you get down to phosphorus or arsenic, all of a sudden those atoms are so big you don't get that electron tunneling through the atom. So we can get chiral phosphorus compounds, but we can never get chiral nitrogen compounds. It's kind of this weird tidbit of trivia. All right. One thing I like to do is label with a star. So I like just doing red stars on these to indicate that, hey, this atom that I'm labeling with this red star is a stereocenter. It's an atom that has 4 different substituents coming off of it. All right, so let's make a note that often, but not always, chiral molecules have 1 or more stereocenter. What's the exception to the not always comment here? Getting back to what we were talking about just a few minutes ago. Yeah, if we have an internal mirror plane. So I'll just put down here, watch out for internal mirror planes. So So this, like I said, is the one thing students most commonly mix up is they do look for these stereocenters, they look for dashes and wedges, things like that, but they forget to check for internal planes of symmetry. So make sure you watch out for that. All right, so let's do a few examples and we'll determine if we're dealing with a chiral compound. All right, so this is one of my favorite drugs. You guys immediately jump to like bad drugs, come on. This is ibuprofen. Look at Dr. Engel doing drugs at home. All right. So, does this have a stereocenter? Let's identify if we have an atom in this molecule with 4 different substituents coming off of it. And if so, where would it be? Okay, so you're saying right here. I would say that has 2 oxygens and 1 carbon attached. So that wouldn't qualify. We have to have 4 different groups, which inherently means we must have to have an sp3 center, right? So no double or triple bonds. What do you think? Carbon immediately to the left, right here. All right, so a lot of people will say, well, there's only 3 groups coming off of that. There's an assumed hydrogen, right? So if we think about this, there is an assumed hydrogen in these bond line structures. So can you see how over here, we've got a methyl group. Over here, we've got a COOH, meaning a carboxylic acid group. Here we've got this giant aromatic group. And then back here, we also have a hydrogen. None of these are identical groups coming off of that carbon, so I agree that that would be a stereocenter. So now let's try to figure out what the 2 possible isomers could be of ibuprofen. So I'm just going to get rid of these green marks just to clean things up. And I'll also get rid of that hydrogen too, just to make things clear. So let's think about this, right? This could exist in one of 2 different handednesses. That methyl group could exist as a wedge coming off of that carbon, right? What do you think the other option is? A dash, right? We'll put a dash in there, and there we go. Interesting tidbit. If you buy ibuprofen at the store, it's sold as a 50-50 mixture of these 2 compounds. This is referred to as a racemic mixture. A racemic mixture is when you have equal amounts of both-handed molecules, right? So in this case, an equal amount of the one on the top and the one at the bottom mixed together. All right, want to see another cool example? It's not really a question, I guess. All right, another cool drug. Also an anti-inflammatory. This one has fused aromatic rings in it. In fact, it looks a lot like ibuprofen. This is called naproxen. All right, so where do you think the stereocenter would be in this one? Same place. All right, so let's try drawing both of these out. Top one, I'll make the methyl group a wedge. And then in the bottom one down here, I'll draw it again and I'll make it a dash. All right. So when you buy naproxen, actually what you're buying is this one. This is the anti-inflammatory. If somehow you ingested the molecule that I drew on top, it will kill you. That's why chirality is important, right? If you're a drug manufacturer, you want to make absolute 100% sure that you're making the right molecule so you don't accidentally poison people. Why do you think the top one might kill somebody? Why would our body care what handedness a drug is? What do you think?
Proteins are designed specifically for specific molecules.
Yeah, proteins are designed specifically for specific molecules. How many of you have learned about enzymes in biology? The classic way of describing an enzyme is lock and key, right? If you have a mirror image of your key, will it fit in that lock? No. So we have to be very, very careful when designing drugs that we account for the correct handedness of the molecule and that we make that drug exclusively over a drug that might have harmful side effects. It's a pretty essential part of the business, and it's not as easy as it sounds to only get one handed molecule while avoiding all of the other. It's a pretty big challenge within chemistry.
Good question.
Yeah.
How do we know that the carbon gets wedged or dashed, not like carboxylate?
That's a good question. So the reality is, so the question was, how do we know that the methyl group's a wedge or a dash and not one of the other groups? The reality is we can choose where we put our wedges and dashes. But the absolute configuration, meaning the 3D layout, needs to match what we're trying to make, right? In fact, let's talk about how to do absolute configurations. It's like you were leading me in. So in the handout, I've got rules for assigning R and S stereochemistry. This is referred to as absolute configuration. To avoid any mishaps, we need to make sure that we clearly communicate to other chemists which handed molecule we're talking about. So, another fun drug, Adderall. Adderall has a stereocenter, square in the center. So I've got that labeled with a star right there. And then what it says is, in step 1, label it with a star. So I'll just make this a red star right there. And then underneath on number 2, it says we want to assign priorities to each substituent based on the atomic mass of the first attached atom. All right, so if we look at that stereocenter and we go one atom away from it, we've got that NH2 group on top. We've got a hydrogen, we've got a methyl group, and then we've got a CH2 group with an aromatic ring attached, right? So if we look at the periodic table, it looks like nitrogen's heavier than carbon, right? So therefore, I labeled that as priority number 1 because nitrogen's the heavier first atom. Make sense? All right. And then when we go out to 2 and 3, this is where it's tricky. Over at 2 and 3, we've got a carbon-carbon tie. So then the question is, well, what do we do if we have a tie situation? So what we have to do is we have to continue looking out. All right, so it's a tie at carbon. If that's the case, we go to the next atom. All right, so if we continue looking out on this CH3 group, the 3 next attached atoms are hydrogen, 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 right? For the 3 hydrogens coming off of that carbon. All right, let's do the one over here. What is that carbon attached to as we continue moving away from the stereocenter? So it's attached to a carbon, definitely. So this carbon right here, it's attached to, what else is it attached to? 2 hydrogens. The other thing you might have noticed is I put this in order of increasing mass to smaller masses. So I put carbon first. All right, so when we look at this, the tiebreaker is going to be the next heaviest atom, right? Because carbon is heavier than a hydrogen atom over here. So therefore, this group right here is going to get priority 2 over the CH3 group, which will get priority 3. And then hydrogen, being the lightest possible atom, is always going to be priority 4 unless we have a lone pair. Does that make sense? So it's a little bit tricky. All right, next thing I always do is I draw an arrow starting at position 1, and then I connect it around going to position 3. So you see how we're going counterclockwise here? or to the left. Anytime we go to the left and our lowest priority is a dash, it's referred to as an S stereocenter. All right, if we go to the right, that would be an R stereocenter. So that's anytime your lowest priority is in a dash configuration. If you notice down here, it says assignment rules are flipped if your lowest priority is pointed forward. So what would happen if we made that hydrogen a wedge and then the methyl group a dash? It would be an R stereocenter. So we do have to account for that flip. And then some students will say, well, what if your lowest priority is neither a wedge nor a dash? It's a little bit trickier, but we have a neat trick that will help us out with it. What I do is I do a Newman projection, where I look down the lowest priority bond, and I draw a Newman projection, and then I can assign whether or not it's going clockwise or counterclockwise. We'll practice this, though, because I know it takes a lot of work. All right, so let's do a few practice problems before getting much further. All right, so the carbon in the center clearly has 4 different groups on it. So I'm going to go ahead and say this carbon, definitely a stereocenter. What would be highest priority? Which is the heaviest first atom attached? Bromine. Okay, so periodic table, bromine's got the highest atomic mass. All right, which would be next? Chlorine. And then third would be fluorine. And then 4 would be hydrogen. All right, so now what I want to do is I want to have an arrow kind of swooping from 1 to 2 to 3. We kind of ignore 4 though. All right, so it looks like this arrow is going counterclockwise, meaning twisting to the left. Does that mean that it's S? No, in this case, we would say twisting left, but our lowest priority is a wedge, meaning this would have what stereocenter? Because normally left is S, it must be R. All right. There's a few tricks you can remember. So normally twisting to the right is an R if your lowest priority is a dash, which makes sense. Right, R. Does anybody know why left is S? This gets into Latin.
Silly.
It's not silly. It's kind of like when you have an oath. Do you ever raise your right or left hand? Right. Your right hand. Does anybody know why we don't raise our left hand? Because it's dirty in a lot of cultures, especially like Arabic cultures, you normally don't eat with your left hand. What else? It's non-dominant, that's another one. In fact, it used to be thought for a long time that your left hand had some like evil qualities to it. So the S is actually from sin rotatory. The same prefix is in sinister. So they used to think like left-handed people had something wrong with them. In fact, when my mom was in Catholic school, she said that the nuns would hit you with a ruler until you wrote with your right hand. So it used to be thought in a lot of cultures and religions that left-handed things were bad or sinister. So if you think sinister, left, S, you can remember that a bit better too. But in this case, it would be an R. All right? Let's do another one. Oops, didn't erase that example. And I apologize if you're left-handed. I don't think you're evil. I think I was reading that there's like a disproportionate number of CEOs that are left-handed, and they're trying to figure out why. So we'll do one of the isomers of ibuprofen. This one has the methyl group as a dash, and that assumed hydrogen I'll just show as a wedge so we can clearly look at this. All right, so what I want you to do is to check with your neighbor and see what you think would be higher priority, and then we'll double check one more time. I guess before we assign R and S, let's maybe work through priorities as a class, because this one gets a little trickier. All right, so if we look at the first attached atom coming off of this stereocenter, I'm going to put dots right here, here, and here. You see how we've got a three-way carbon tie? First attached atom off of each of those substituents is a carbon. What do we do in a tiebreaker situation? Yeah, we can keep going, or we can say, all right, let's look at this carbon. What is it attached to as we work further away from that stereocenter? So in this case, it's attached to 2 carbons. However, what we need to do for double bonds is we essentially count that connection twice. This is called a ghost carbon. So count double bonds twice. All right, so we've got that figured out. Now let's go over here. All right, what is this carbon bonded to? So it's bound to 2 real oxygens, right? So 2 oxygens are definitely attached to that carbon, but you see how we've got that CO double bond? That means we need a ghost oxygen as well to say, hey, this is the second oxygen from that double bond. We count that bond to oxygen twice. All right, then we'll go over here. What's this carbon bonded to? 3 hydrogens. All right, so now let's work through the priorities. Which one would be number 1? The carboxylic acid, right? So I'd say, all right, this is priority 1. And then over here, this must be priority 2, priority 3. Hydrogen would be priority 4. So I'm going to swoop from 1 to 2 to 3, like that. Are we twisting right or left?
Right.
So think about how we're twisting, right? We're twisting it clockwise or to our right. So the arrowhead is going in the right direction. All right? So does that mean it's an R? No, it would be an S, right? Why would it be an S? Hydrogen's a wedge, right? We only stick with the normal rules when our lowest priority is a dash. Anytime our lowest priority is a wedge, we flip-flop things. Okay, so let's make a note here. It's twisting right. But our lowest priority is a wedge. Therefore, this will be an S isomer. Make sense? It's a little bit confusing. Let's try another hard one. We'll just do a challenging one, and hopefully it'll make more sense with this challenging one. Okay. I'm forgetting the name of this drug, but I think it's an arthritis drug. All right, so where's the stereocenter? Middle carbon right there. All right, now we've got to determine what's going to be highest priority. So check with your neighbor and see if we can agree on the highest priority. All right, so let's do this as a class. So over here, I'm saying this first attached atom off of this position is a carbon, right? First attached atom off of this position is a hydrogen. First attached atom off of this position, a nitrogen. And then first attached atom off of this position, be a carbon. All right, so which one's going to get priority 1? Nitrogen. Okay, so I'm going to say nitrogen is going to be number 1. Just put a 1 there. All right, so we've taken care of our nitrogen 1 being priority 1. All right, I'm seeing a carbon-carbon tie, though. It's problematic, right? What do we do? Okay, so we'd say, let's focus on this carbon right there. What is that carbon attached to as we move outwards? It's attached to a sulfur and 2 other carbons, right? So underneath this, you can say, all right, sulfur, carbon, carbon is attached to that specific carbon. All right, now let's do the one over here. What is that attached to? 3 oxygens. And 1 is a ghost because we've got that double bonded oxygen, right? So we count that bond to that oxygen twice. All right, so now we've got to go to the periodic table. And remember, we want to first find our tiebreaker. So what I do over here is I say, all right, the heaviest atom in this grouping is sulfur. Heaviest atom in this grouping is oxygen. So which one's going to win? Sulfur. Okay, so we can go ahead and we can say this is priority 2. That means that this must be priority 3, and then hydrogen is always going to be priority 4. All right, so now we've got this more or less worked out. We can go 1, 2, 3. Does that make sense? So is this to the right or to the left? Yeah, so if we look at this, we're twisting it to the right, but what would the configuration be? S. Okay, so let's make a note. So we twisted to the right. But our lowest priority was a wedge. Therefore, this would be an S stereocenter. Does that make sense? So these tiebreaker rules do get kind of tricky, but I do want you to keep in mind ghost carbons apply. What do you do if you have a triple bond? You have 2 ghost carbons, right? So then you count the bond to that atom 3 times. So we need to look for tiebreakers. We need to look for ghost atoms, meaning double or triple bonds. And then we also need to watch out for the situation where our lowest priority is a wedge. If it's a wedge, we need to account for that and then flip our assignments from R to S or S to R. Make sense? All right, so remember, if you are in Thursday lab, we are meeting right now. We'll go upstairs. If you forgot your herbs, that's fine. We have backups. Friday lab, we are meeting tomorrow.